Thank you. Great to be here. And yeah, that build-up is there as to what we're going to talk about. It's hard to think about on a day like today, but you know, the planet's warming. I think this is a nice visualization to really show us what's happening over time rather than just looking at a plot of the temperature rising. But it's clear this is a problem. It's recognized actually by the AMA, the the Medical Association, the Heart Association, the World Health Organization as really the biggest public health challenge of the 21st century. And we've seen all these problems from fires and droughts and storms, all of those things. And for a lot of us, you've been hearing about climate change for so long, and it seems like an overwhelming problem. And sometimes I hear from students, there's kind of this despair about how we're going to get past this. And what I want us to realize, first of all, is that we have faced enormous problems like this in the past. And as a society, we've solved them through science. And so by way of that, I'm bringing up this example of learning from history. This is a wonderful book called The Alchemy of Air by Thomas Hager. He's a fabulous writer. And basically, it's going to tell you a longer version of the story I'm going to very quickly tell you today about the Haber-Bosch process. But basically, world population was increasing, and there was worry that there wasn't going to be food. This was kind of, and a lot of people believed this. And then you had the naysayers, just the same way you have them today, that climate change is not real. Okay? Now, in 1898, Sir William Crookes was giving his inaugural address as the president of the Royal Academy of the Sciences. And what he said was that England and all civilized nations stand in deadly peril of not having enough to eat. And basically, the prediction then was that there would be mass starvation by the 1930s. There wasn't. That didn't happen. So what's the deal here? Well, it turns out that fertilizer that they needed to grow all this food for the growing population was running out. Now, in the 1840s to 1870s, the fertilizer that everyone sought after was basically bird guano. So there were these islands, the Peruvian islands, that were covered in bird poop. And this was an incredible fertilizer, and boats would come up to these islands, and they had people shoveling all of this bird poop onto the boats, and they were crossing the Atlantic, and everybody was in need of this fertilizer. Now, it's clear that it took the birds a long time to make all of this stuff, right? And we dug it out in a matter of 30 years. Well, we were lucky, actually. Oh, I should say you can still buy seabird guano if you want from Amazon. It is wonderful fertilizer. But we lucked out because then in about the 1870s to the 1920s, we discovered these nitrate reserves in Chile. And so then that became kind of the new place where people were getting fertilizer. But you can see then this is running out. So what was going to happen then is there were going to be all these people who had no food to eat because we didn't have enough fertilizer. So what Crook told his audience is that we needed to use science to figure out a way to make fertilizer. So it's the chemist here who must come to the rescue. The reason that he picked out the chemist is because the key to fertilizer here is nitrogen. And so what we needed to do is find a way to get more nitrogen that the plants could access. Now, where's the most nitrogen? Well, the most nitrogen is actually in air. It's all around us. So air is almost 80% nitrogen. So nitrogen is here. It's two nitrogen atoms bound together, and what you're going to see here is there's three lines here. That signifies a very strong triple bond. So those two nitrogens are held very closely together, and that's not a form that's easy to use for fertilizers. It's not easy for the plants to access. So what we need to do is fix it, break that apart, and get that nitrogen in a form that the plants can easily use. So that's exactly what happened then. And it's important to realize here that this invention of the Haber-Bosch process, this is Fritz Haber, who was a chemist, Karl Bosch, who was a chemical engineer. And in Germany in the early 1900s, Fritz Haber developed a catalyst, and we'll talk more in a little bit about what a catalyst is. But they found a way to break this bond, very strong bond, break these bonds between hydrogen and fix the nitrogen here, the blue one, with 3 hydrogens around to make ammonia. And many of you will realize ammonia is a very powerful fertilizer. And you see, if you're in the Midwest anytime, you'll see big trucks with ammonia going around being used for fertilizer. This was really the most important technological advance of the 20th century. It wasn't the computer or anything like that. It was this process. Okay? 2 Nobel Prizes here for these folks. Why is it the most important technological advance? Well, it's because half the people on the planet would not be alive without this process. So we're now at over 8 billion people. Half these people wouldn't be alive. It's estimated that over 50% of the nitrogen in your body has actually gone through this Haber-Bosch process. Okay, so the lesson here is that we've faced massive world problems like this before, and we've solved them through science, well, through chemistry and engineering. Okay? So that's one way we're going to take into this problem of climate change. Because in many ways, it is a very similar problem. It has to do with small molecules, just like we saw with nitrogen and hydrogen to make ammonia. So this is a natural greenhouse effect, right? We have the sun warming the earth, and the earth re-radiates that heat, and then lets some of that escape, and then some of it doesn't escape because it's trapped by these molecules that are in the atmosphere. We need this natural greenhouse effect. If we didn't have these molecules in the atmosphere, then we couldn't live on the planet, right? This keeps us at a temperature where we can live, we can grow things, we can have a nice life. The problem is that we've put too many of these small molecules up into the atmosphere, and they're trapping too much of that heat. They're absorbing too much of that heat. And primarily what we hear a lot about is CO2, and that's because we see plots like this. So this is showing along here, this is the average temperature in the 20th century. And so you can see, just like that plot, the movie I showed in the beginning, the temperature's clearly rising. But what you also see superimposed is this black line, which is the carbon dioxide levels. So it really looks like there's a pretty clear indication that the CO2 is the problem here, right? And you can see then, here's the CO2 line. This is increasing. You can see the fluctuations here with the times of the year, but you can see here's the CO2 levels. And then on this side, what we're seeing is the fossil fuel emissions from, the fossil fuel carbon emissions. And the black line here is the total of all of these. So the other lines you're seeing here, for some reason they put green for coal, but so this is coal, this is petroleum, this is natural gas, and this is actually cement. And when you stack all of these on top of each other, that's where you're getting the black line. Okay, and you can see that it very well matches this CO2 line on the other side. So it's pretty clear the problem here is our energy use, that we're using all of these things, petroleum, coal, natural gas, to get our energy. So let's take a little bit look back on how we've been using energy in the United States. So this is United States energy consumption from the beginning of the country to now, basically. Okay, so in the beginning of the country, 1776, so it always feels right to be talking about this in Philadelphia because that feels like a real start of the country here. So this is where we're using primarily biomass, so that's wood, right? That's going along here. In the 1850s, this is really the start of the Industrial Revolution. We start using coal. The early 1900s, we discover oil, and then that picks up and actually crosses coal in about 1950. It's followed quickly by natural gas here, and then that goes out to this. We also see nuclear comes in after World War II and then kind of levels out. But what you're seeing here is the renewables, and the growth here you're seeing is solar and wind at the end, right? It's not nearly steep enough because this part of the plot here, remember, these would all be stacked on top of each other to show us our total energy use. So this renewables is only a tiny piece of the puzzle at this point. The other thing you'll note here is this very dramatic uptick in natural gas versus this downward trend in coal. That was very deliberate. So from the 2010 to 2020, there's a deliberate effort to switch over the coal-powered power plants to natural gas. And that actually had a really big effect. So you can see here in the United States, that gave us a net negative in terms of our CO2 emissions. That's great, but then you realize, well, unfortunately, there are all these other countries that increased. And it is really a global problem. Okay? So that's not going to be enough. But that's all looking at the past. What we want to do is really look at the future. So here we are looking at the future. This data was from 2021, and I'll talk about why I'm using that data in a minute. But this is where we're projected to be. So you can see here out to 2050, we're still using as much, if not more, petroleum. We're still using as much, if not more, natural gas. Renewables is coming up, okay, our solar and wind, but not really steep enough as the way we would hopefully want to be. Nuclear staying kind of flat, coal here. So really the key here is that the situation doesn't change much. I mean, we're going to be using more energy that's coming from renewable energy, but here we're not really making a big change. So it's really hard to think about people saying that we're going to be carbon neutral by 2050. I mean, there's just no way when you look at these kinds of predictions. So then you have to ask yourself, well, okay, well, what are these predictions based on? Well, on the one hand, they're based on current laws and regulations. And so that's why I think it's really exciting that at Penn we have the Climate Center for Energy Policy to try to get real data and concepts into our legislators. The other thing it's based on is incremental advances in science. So just as the way our memory sticks kept being able to put more and more memory on a stick, that's an incremental advance in science. What we really need are step changes. And really that's what the Vagelos Institute is about. It's really about how do we lower these lines and raise up our renewables line. Now, I said that this was all based on old data. But I will point out, this dip here, that's COVID. It's incredible that it comes out there. But the reason that I based it on old data is I don't know where the new data is, because we look at this, and then we see just in the last few months, Trump spending $625 million on coal. The Trump administration redirects carbon capture funds to prop up old coal plants. So I don't even know where those predictions are going now. Okay? But we have to take solace in that we're only in the United States, and as I said, it's a worldwide problem. So let's think about this more on a world scale. So I really like this graph because on this side it shows the Human Development Index, and on this side it shows the energy demand per capita. And what you see is it's basically a straight line. If you want to move up on the Human Development Index, you're going to have to use more energy. And the other thing you're going to note here is that the size of these circles are based on the population. So here's the United States, up here, a very high Human Development Index, but we're also using a very large amount of energy. The only one who, a few that are higher, Iceland is up here. We'll come back to Iceland, so remember how much energy Iceland is using. Now here we have India and China, very large populations. As these want to move up, they're going to have to use more energy. So what does the energy projections look like for the world? Well, they look a little bit better than the US in that the renewables line is higher. But again, look at the petroleum. It's not going down. Okay, so this is then a problem to think about, is how are we going to reduce these amounts? And it's the other part to remember is it's not just energy that we actually get from petroleum. Okay? even if you don't drive or fly, you're actually using oil every day. So if this pie chart was a barrel of oil, most of it is used for transportation. Okay, so for fuels, for gasoline, for jet engine fuel, all of that. But this 14% up here, that's used for petrochemicals. And petrochemicals are used to make everything. You know, the carpet here, the seat cushions, the plastic here, the clothes many of us are wearing, the body care products you used this morning, the medicine that you took this morning, all of our medical supplies, your clothes, all of this is coming from petroleum. And the reason that we have it and at the cost that we do is because we refine all that gasoline. And this 14% is really a byproduct of gasoline refining. So the question becomes then, as we move towards using less petroleum, where are we going to get all this stuff? Well, just like the common denominator in fertilizer was nitrogen, the common denominator to all those things is actually carbon. So it's a little bit of a misnomer when we talk about decarbonizing things, because we still need all that carbon. Okay? It's just not getting it from the same sources. So we need to think about using methane and natural gas liquids. I'll come back to this because you saw on that plot we wanted to try to use less methane, but I'll explain what methane I'm talking about here. We want to think about how to use non-food biomass, so things that are not going to affect, we don't want to starve people. We're talking about using lignin, waste oil, the corn stalks. We could talk about CO2. CO2 is obviously a problem. It has carbon in it, though. Could we use that? And then a big one that's come online recently is people have started thinking about using plastics because there's a ton of carbon all in this. Okay, so let's start with methane and natural gas liquids. So if we start here, natural gas, as you think of, like shale gas, is mostly methane. So the predominant part of natural gas is methane. Methane is a small molecule that looks like this. There's a carbon in the middle attached to 4 hydrogens. There are some higher alkanes that are in the mix. The Marcellus shale gas in Pennsylvania is about 16% of a C2 ethane. But it's not just, the natural gas is not just in these gas deposits. I want to point out, first of all, that methane is about 80 times worse than CO2 in terms of warming, in terms of its warming potential on a 20-year time frame. It's been estimated that about up to a third of climate change, of warming, is actually caused by methane. So it's really a considerable thing to think about. We do have a lot of methane emissions that are not just from these big stockpiles of methane. You can see here that this is natural gas here is about 33%, but then enteric fermentation is a large part. Landfills are a large part of our methane. And all of this is contributing. Now, the other part about this comes from looking at a picture like this. When you look at a picture like this, everyone can clearly tell it's the United States. And what you're looking at is light pollution. Okay? And you can see all the lights from all the big cities. So here's the eastern seaboard with New York, Philadelphia, Washington. That's clear. You might not be as used to looking at the Midwest. So I'll point out this is Minneapolis up here. This is Chicago. This is Denver. This is North Dakota. So what large city is in North Dakota? Well, there is no large city in North Dakota. So what is all this light pollution from? This light pollution is actually flaring natural gas. So this is natural gas that's being flared here simply because it's coming up with the oil production and it's too expensive to bring it to market. So it's too expensive to transport it because you either have to cool it or build a pipeline, and since gas has a very low density, it's very expensive to transport. So what you end up doing is burning it. And the reason that this is being burned is because, as I said, methane has a greater warming potential than CO2. So the companies are kind of doing us a favor by burning it. Now, This is not something that's just happening in North Dakota. We also flare a lot in Texas, but this is no longer light pollution. This is showing you the flaring of natural gas all over the world. In 2022, 139 billion cubic meters were flared. So this is just being converted to CO2 for no other reason than to prevent the methane from escaping. So the question is, could we actually take this methane and use it to make something useful so that we don't have to be using so much of our, so many other sources to make those chemicals and fuels? Well, the idea would be to convert it to a liquid, because once you convert it to a liquid, its density is such that you can move it, and that then becomes economically feasible. So the goal would be to convert it to methanol, which is another simple chemical, but it's a liquid. So what happens is, the current technology, and that's actually how we do make methanol. We take methane gas and we do a reaction called steam reforming, where we take methane with water at very high temperatures. So if you look here, 700 to 1,000 degrees, to make carbon monoxide and hydrogen. And then we take those two chemicals together, carbon monoxide and hydrogen, over a different catalyst at 250 to make this molecule methanol. And so this is a very intense, energy-intensive process to do this. Costs a lot. It also requires, in order to be economically viable, you have to do it on scale, which means you need a $1 billion plant to run this process. So there's no way you can think about building one of these $1 billion plants in every place we saw those flashing lights. So instead, you'd like to find a way to do this reaction better. And this reaction was created, in the last century. We're going back to like Haber-Bosch times, right? We didn't know as much chemistry as we do now, because this is not the way you would try to get from this molecule here. If you look at it and think about it as a ball and stick form here, if I was going to go from here and I was going to take things apart and put them back together again, and I wanted to get here, I can guarantee you, if I gave you these ball and sticks, you wouldn't first rip all of these off, get to here, and then go back and put it all together again, right? You just want to break that one bond and insert an oxygen. So what we'd like to do is this reaction right here. Break one CH bond, insert oxygen, and get to methanol. And if we can develop a catalyst to do this the same way that Haber did to make ammonia, then we could run this potentially at a low energy process, small scale. Maybe we could even have portable methanol plants. So we could drive up to landfills even and convert that methane to methanol. Drive up to all those sites you saw the flaring gas. Okay, so in order to do this, we need to develop a catalyst. So then the question is, what's a catalyst? Well, in general chemistry, some of you might remember back to when you took that, if you took it, which you don't have to understand this. But basically, to get a reaction to go from reactants to products, you typically go over this barrier here. So you have to go up in energy and come down. And if you have a catalyst, you go by this lower energy pathway. Now, those of you who didn't take chemistry, I'm going to just explain it a different way. Let's say you were really hungry. If you're really hungry, you're at a higher energy, right? You're hangry. You're at a high energy state. And you want to be fed. That's when you're nice and relaxed and peaceful. Okay? So if you want to get to that state, you're going to have to make yourself dinner. That's an energy barrier, right? Because you have to get up off the couch and you're going to have to make this dinner. Now, what if instead you could order dinner? Now you have lowered that energy barrier. You've taken a different pathway, but it's lower energy. You had to decide which restaurant, you have to make some decisions along the way, take some steps. Which restaurant, what to order, you have to pay the delivery person. You do this all with your phone. Your phone is actually the catalyst for this reaction. It got used in the reaction, but it didn't get used up. Okay? So it's the catalyst for this. And I want to credit this. This is not mine. This is Joshua Kritzker at Tufts that I stole this. But I think it perfectly illustrates what catalysis is. So in a cycle from methane to methanol, what we're looking at is trying to first just break one CH bond, as we show here, to put the carbon with the 3 hydrogens on the metal center. And then we want oxygen to come in here and insert between the metal and the carbon. And then in the last step, have functionalization to release our product. So in this reaction, this metal species, this is like our cell phone. This is our catalyst. It doesn't get used up in the reaction. We just keep bringing in new reagents. We keep ordering dinner here, and we keep eating our dinner on this side. Okay? So some of the, this would be just one of a couple slides where it shows this would be the type of complexes that we're looking at here. We activate a CH bond, insert oxygen, get off our product. This isn't yet a good working cycle, but that's some of the things that we're working on in the lab. These are some of the former Penn students who worked on it, and these are some of our current Penn students who are working on this problem. Okay, so talked a little bit about methane and natural gas. Let's talk about CO2. What we'd like to do with CO2 is set up an anthropogenic carbon cycle. The idea here would be that we take CO2 and we would hydrogenate it to make methanol. So we're making methanol again. Methanol is like this platform chemical that we can take on to make a lot of other chemicals and fuels, and that's what's shown here. Then we can take these fuels, we can even burn them, we capture the CO2, and we go around this cycle. So we're not contributing to more CO2 in the world. We're just recycling it. Well, there actually is a plant in Iceland, remember Iceland, that takes CO2 to methanol. It's called the George Olah Renewable Methanol Plant. It does this reaction here, uses a catalyst, this copper, zinc oxide, aluminum catalyst. It operates at greater than 200 degrees. This reaction, and here, for people who took your general chem, you'll see from delta H and delta S values here, you can calculate that this reaction runs farther and farther to the right, the lower and lower you have the temperature. So basically what it's saying is we get more product if we can run the reaction at lower temperature. So what we're looking for are new catalysts that will promote the reaction at lower temperature. This plant operates in Iceland. We can't build these plants in other places because Iceland has an enormous amount of geothermal energy that lets them make the hydrogen to run this process. And in fact, if anyone has anyone ever been to the Blue Lagoon Spa in Iceland? Okay, we have a winner there. You're actually bathing in the industrial wastewater from the geothermal energy plant. It's okay. It's perfectly safe. It's clean. I mean, it has a lot of minerals in it. It's great. But it is funny that they have this ridge here, so when you're in the water, you don't actually see the plant there. Okay, so if we want to do it at lower energy, what do? Well, we can use nature for inspiration. And nature does this, right? It fixes CO2. It does this photosynthesis. It uses protons here, and it gets electrons from NADPH, and it fixes the CO2 to make, in this case, acetic acid. And it does it by this remarkable process here, which I don't understand, but that's not the point of this slide. The point is to show you that the way nature does this is by taking, these are all these different steps are individual enzymes that are, they're individual catalysts that are working in sequence. So the first one takes your CO2 to formic acid here, and then another enzyme comes in and converts it down, and so on down the line. They keep passing off that species. So in being inspired by nature, Melanie Sanford at the University of Michigan came up with this idea that we could take different catalysts that were known for each of these different steps. And so there were known catalysts that could do this first step, and then she could use a known catalyst in the second step, and then a known one in the third one. And that's what she did. She used these 3 catalysts here, and she did this reaction, and she found out she got a turnover number of 21. What is a turnover number? It's how many times you get around the cycle before your catalyst dies. So if you think about it, it would be like if you could order dinner 21 times, and then you had to get a new cell phone. Okay? So not all that useful. But nevertheless, this was a remarkable advance because nobody had ever gotten anywhere near that number before. So the next thing you want to know is why did the telephone or the catalyst die? And it died because it turned out that one of these sites on this catalyst C was actually sensitive to acid. And this catalyst B generates acid. So it turns out catalyst B and catalyst C are incompatible. So in our lab, we had actually been working with that third step, the last step of the catalytic cycle, and we found a different catalyst, which is this one shown here. Which is this one shown right here, this iridium catalyst. And what we found was this catalyst C worked even better when we put catalyst B in there. So wow, this is looking great. It seems like all we have to do is take this and put it in Melanie's system. So we tried that, and we didn't get any turnover. So now our cell phone doesn't work at all. So what's the problem? Well, we worked out that it turns out that catalyst A is now incompatible with catalyst C. So what happens is these phosphine ligands, these PME3 groups, fall off this metal and end up attaching to this iridium, which deactivates it. So catalyst A is now incompatible with catalyst C. So what we decided to do was tie these phosphines onto the metal center, so kind of build a structure like this where the PME3 groups couldn't leave the metal center. And that's what we did here. So we used a different catalyst A, and when we did this, we got less than 10. So we're better, that's better than 0, but we're not even up to where Melanie was. So what's the problem here? Well, we worked out that this catalyst is actually too slow. And we needed a faster air-stable catalyst C. So we did that, and we found one as shown here. This is an iridium complex, a different one. Now we got over 420, and I point out here this work was done by a postdoc, Amy Chu, a Viper undergraduate here, Bernie Wang, and a graduate student, Zuzana. So 420 is good, but it's not really, you're not going to get rid of your cell phone after 420 dinners either, right? So in work then that built on this, and that's the way science works, right? We keep building, was Jeff Byers actually took catalysts and he enclosed them in what are called MOFs. That won the Nobel Prize last year. These metallic frameworks where you could drop kind of like little cages for the catalysts. So he put them inside these little cages, and now he can get turnover numbers of 100,000. So that's sounding a lot better. But there's a problem with all of this chemistry, and that problem is that the hydrogen that we're using is currently sourced from methane. The hydrogen that we use in all these chemical processes comes from that first reaction I told you that was really high in energy, right? It's from methane reforming. So there's been a lot of work, as shown here, trying to take water and use sunlight to make hydrogen and oxygen. A lot of that's still in progress. But maybe we don't need to make hydrogen at all, because back from Gen Chem, we can remember that hydrogen is really just 2 protons and 2 electrons. And that's actually what nature does. It takes protons and it gets electrons here from NADPH. So with that idea in mind, the Department of Energy in 2020, and luckily this was renewed in 2025, we were very worried about that, but the Department of Energy has invested $200 million in 10 years to do this artificial photosynthesis. So to take CO and water and sunlight and make liquid fuels. And there are 2 large hubs. One's called LISA, and the other one's called CHASE, or the Center for Hybrid Approaches in Solar Energy to Liquid Fuels. And this is one that we work with. The idea here is to have a semiconductor where the catalysts are attached to the semiconductor, and the semiconductor absorbs light. So this is a lot of what, if there are any of my Gen Chem students in class, in here from class today, we talked about light is absorbed by the semiconductors. It then releases these electrons, the separated charge in the semiconductor, and those go to these catalysts. My group is working on designing what these molecular catalysts are doing, but there's, and then we again have to worry about how the catalysts work together. So just like we saw with the other system with hydrogen, the catalysts all have to be compatible, but they also have to pass everything off in the proper rate. They have to all act at the right rate. So it's complicated to get these systems together. You need people who know about semiconductors. You need people who know how to attach the catalyst. You need people to know how to characterize all of these things. And so what this involves is a huge collaboration. There are 26 PIs in this center. A lot of early career researchers. Those are graduate students and postdocs. At Penn, we have 4 of our faculty here in both chemistry and Cs. And you can see then we're located all across the eastern seaboard here. Okay, so the last one I just wanted to mention then is plastics. Some of you will get this next joke. Some of you won't. Depends on your age. So there's a great future in plastics. From the graduate, there's so many benefits to plastic. We rely on it so much for everything from lighter materials for transport or medical apparatus, food storage. But we've all seen the bad side of plastics, right? The accumulation in the oceans. We think we're doing a great job here by putting our recycling in these bins. But the truth is, very little of this actually gets recycled. So when you look at a plot like this, you can see that the amount that's recycled is in green here. This is incinerated, and all of this is discarded. If you look to the future, and we're using a lot of plastic. This tells you how much plastic we use a year in the US. But if you look to the future, you can see that this discrepancy between what's recycled and what's discarded gets even bigger. Okay, so as we said, very little gets recycled. This shows you the US recycling rate. But what are then these plastics? If we just look at polyethylene, so polyethylene is just a carbon chain with hydrogens. So this actually looks a lot like methane, except instead of just having 2 hydrogens attached, now the other 2 bonds are to other carbons. So a lot of the same methods that we're using to activate for methane maybe can be applied here. This is showing a molecule of linear polyethylene, a milk carton versus low-density polyethylene here. Here that's more of these wrapping kind of plastics. So what we're trying to do is develop catalysts that can convert this into chemical and fuels. And this is a funding that was originally started as a seed grant through the Vagelos Institute and then went on to earn DOE funding. This is an effort led by Karen Goldberg and Cs. Again, it's a collaboration between engineers and chemists, just like the Haber-Bosch process, right? And so what we're trying to do here is develop catalysts where we can dehydrogenate, break those CH bonds, make hydrogen here. These can be depolymerized, and other groups are working on that. The polyup strategy is to take these dehydrogenated material and convert them to more functionalized materials. And these are now value-added polymers that can be used as adhesives, as sealants, insulation, all of these things from that discarded waste plastic. Okay, so what I hope I've shown you here is that really the effort is to completely disrupt the chemical industry and liquid fuel industry. So stop getting it here from petroleum and think about ways that we can get the carbon from all of these other sources. If we can do that, then we can change what these plots look like. But this is going to take, first of all, new regulations and policy, which hopefully in the midterms we can think more about that. And on the other side, it's going to take big advances and investment in science. And it's clear that multidisciplinary approaches are key to this. It's not going to be chemists just working together. It's going to, and that's the beauty of the Vagelos Institute, is that it brings together engineers and chemists and physicists. And so here's a picture of our new building. I encourage you to come by and visit us here at the Vagelos Laboratory. This is located right next to the ice rink. We just earned platinum status, LEED certification in platinum. These were the agencies that we get a lot of our funding from, my incredible research group, and I also want to thank my wonderful collaborators at Penn and outside of Penn. And thank you for your attention.